The LATT, standing for Large Aperture Telescope Technology, is a strategy for space-active optics, to compensate for in-orbit optics and mechanics thermal bending. In the LATT, the deformable surface is a lightweight primary mirror, featuring ultra-thin glass shell actively shaped by voice coil actuators in closed loop. Within the LATT, we updated the concept of adaptive secondary mirror, as those equipping the large binocular telescope, to fit the requirement of a space telescope. The technological and operational expertise from ground-based HAW was a valuable background in the development of the LATT. How does a LATT primary work? A 1mm zerotter glass shell is the optical element. An ultra-lightweight reference body is the support structure for the voice coil motors, which apply an electromagnetic force to magnets glued on the shell back. This way, the actuators provide a contactless shaping of the optical surface and keep the desired position thanks to closed loop fed by capacitive sensors. The concept of the adaptive secondary has been validated since many years. To demonstrate its applicability to space telescopes, two main challenges were faced during the LATT project. Will the shell survive to the launch accelerations? Is it possible to control the surface shape with very low actuator density and power budget? We have assessed these questions through the LATT optical breadboard, a 40 cm diameter spherical mirror prototype. In the OBB, the shell is 1 mm thick and the reference body is an aluminium honeycomb layered with carbon fiber reinforced plastic. Thanks to this technology, the aerial density as active primary resulted as low as 17 kg per square meter. The OBB is controlled by means of 19 actuators with a typical power consumption of 50 mW per actuator. They are able to provide a stroke of ±0.5 mm, thus allowing the deployment and phasing of the petals of a segmented mirror. To make the shell resist the launch, the LATT team developed an electrostatic locking mechanism which has been tested on a vibration stand to simulate the shocks. The electrostatic locking glues firmly the shell on the reference body during the launch phase, thanks to an electrical field between the shell and the reference body. After the launch, the lock is released to allow normal operations. We also demonstrated the optical controllability of the shell surface, although with a very low actuator density and power budget. The achieved wavefront error is 26 nanometer mRMS, comparable to the flattening result obtained with the adaptive secondaries, with the same actuator geometry. The flattening procedure is based on the correction of the mirror stiffness modes, which are measured to build up the optical interaction matrix. After flattening, we run stability tests to make sure the optical surface quality is preserved during operations. Thanks to the OBB, we assessed the technology for a lightweight primary mirror, with contactless wavefront correction, for space telescopes. The LATT offers a fail-safe optical control, with low power consumption and very large actuator stroke. The LATT is suitable for segmented apertures, actively controlled and co-phased, opening the way to the extremely large space telescope.